Thank you very much for introduction. It's working? Yeah. Okay. So today I'd like to introduce an interdisciplinary study between the particle physics and astrophysics that we have at the Kavli IPMU. And actually, this is my collaborators, and which include both particle physicists and also astrophysicists. And actually, the main goal of this study is to detect some type of the WIMP, where it is very close to the SU2 gauge eigenstate of the standard model, SU2 gauge interaction of the standard model. Well, in other words, weakly charged WIMP. So, and actually, this study, the motivation is coming from the particle physics. So first, let me explain that what real motivation is. And actually, this is a study of the very traditional dark matter candidate, WIMP. And the WIMP is very, how to say, is a broad concept. And there are many possibilities of the WIMP before LSC. Was many possibilities before LSC. And, but recently, a kind of the serious test of the WIMP has begun. And especially, which is by LSC collider experiment, and also the underground experiment, or in other words, a direct detection experiment at the underground facilities. And actually, because of these two experiments, some part of the WIMP candidate is now being excluded. But still, there are several types of the WIMPs, which is not searched for enough in a robust way. And one of the examples is, for example, the light WIMP case, like whose mass is less than 1 GeV, or also the leptophilic WIMP is not searched for in a robust way. But today, I'd like to focus on the so-called weak charged WIMP, meaning that WIMP has a weak charge, or to be more precisely speaking, the WIMP is described by the quantum field, which is very close to the SU2 gauge eigenstate. And actually, this WIMP is very well motivated from the viewpoint of the new physics models describing electroweak symmetry breaking. For example, in the supersymmetry, after the LHCs, many people, many people became interested in some type of the Suji scenario, which is sometimes called a mini-split type scenario, like this one. So meaning this scenario is actually, how to say, some gauginos, fermionic superpartners are predicted to be order 1 TeV. On the other hand, other particles, like squarks and leptons, are predicted to be much higher than the TeV. And especially in the IPMU, a concrete model has been proposed before the Higgs is discovered by Yanagida-san and Ibe-san. And this is nowadays called the pure gravity mediation model. And of course, its phenomenology was carefully studied after Higgs discovery. But in addition to that, of course, around the world, there are many concrete scenarios how we propose, all of them are also predicting the same spectrum, or at least a similar spectrum. And also, I'd like to mention that in addition to the Suji scenario, so recently some people discussing some other type of the new physics models concerning the electroweak symmetry breakings, which also favor this type of the WIMP. And the big question here is that how we can detect this kind of WIMP, or to test this kind of models. And so in order to answer to this question, so first let me summarize some properties of the WIMP of this type, and assuming that WIMP is fermion. So because these scenarios predict the fermionic dark matter. And the first property is the mass of this WIMP is predicted to be around 1 TeV, and also degenerate with its SU2 partner in mass. Because of this reason, that this WIMP is very hard to be detected at collider experiment in near future. Of course, once we have 100 TeV collider, so we can detect this one. But this kind of huge detector is very hard to be realized in near future. So next, this WIMP scatter of a nucleon only through the loop diagrams, because this type of WIMP doesn't have a direct interaction with the Higgs. And because of this fact, and the essential reason is that because that WIMP is very close to the SU2 gauge eigenstate. But the most important thing is that this WIMP is also very hard to be detected at the direct detection experiment in near future. Of course, if we have a third generation direct detection experiment, this type of WIMP may be detected. But again, this kind of the huge underground experiment is hard to be realized in near future. And the last one is that so its annihilation is boosted by so-called Zomba-Peltier enhancement I found a long time ago with Mihoko and Junji. And because of this one, the annihilation cross-section becomes very huge compared to the usual WIMP case. And then we can expect that this WIMP can be effectively detected at indirect detections even in near future. So let me focus on the indirect detection of the dark matter. Okay. So this is actually the motivation. So this WIMP is very attractive, and I want to hunt this kind of dark matter. So what we should do? So focusing on the indirect detections. And actually, there are so many types of the indirect detection experiments. And sometimes people use the cosmic rays, gamma rays, and neutrinos. But among those, the most robust way to detect this WIMP in the direct detection experiment is the use of the gamma ray observations, especially observing the gamma ray from the WIMP annihilation in satellite galaxies called dwarf spheroidal galaxies. And the reason is the following. So because first, so we can expect enough strong signals because these satellite galaxies are located very close to us. And also, they are known to be very dark matter-rich astrophysical objects. And next, the background, again, gamma ray background against a signal is also weak. Because there are very few astrophysical activities inside the galaxies. And actually, the main background is coming from cosmic rays, cosmic ray-induced gamma rays, actually. So because of these two reasons, the gamma ray observations from the dwarf spheroidals is, I think, the best way to detect such a WIMP dark matter. And actually, this is a picture of the dwarf spheroidal galaxies, about its locations, which is this figure is used in Wikipedia. And this is our galaxy. And actually, we have so many satellite galaxies, dwarf spheroidal galaxies like this one. And we are focusing on the gamma rays from these directions. And in the signal, so we have to calculate the flux, gamma ray flux. And this is actually the flux formula, but details is not so important. The point is that this flux formula is composed of two components. One component is coming from particle physics. And the other component is coming from astrophysics. And on the particle physics side, actually, so we can carefully calculate the annihilation cross-section or so-called fragmentation functions using the perturbation theory usually. On the other hand, the astrophysics factor, which is called the J factor, so, and it's very difficult to be estimated at present. And in fact, this J factor is, roughly speaking, so this is a kind of the density squared of the dark matter inside the dwarf spheroidals. But in order to detect this type of the WIMP, or at least put a very robust limit on its property, so it's actually mandatory to have to estimate the flux very accurately. But as I said before, so the estimation of J factor is a very hard task, actually. And now still we have a large uncertainties, large systematic uncertainties at present. So we want to improve these situations with astrophysicists. Okay, now, so this is the actually particle physics aspect of these studies. And I want to go to some astrophysical aspect of these studies. So how we can estimate the J factor in each dwarf spiral galaxies. And actually, this is is representing some how to estimate the J factors in a mathematical way. And this is obtained by simply comparing with theory and experiment, of course, as usual. And at the theory side, so starting from the so-called collisionless Boltzmann equations, we can derive the so-called Jeans equation. So which is differential equations describing some distribution of the member stars living inside the dwarf spiral, living in the galaxies. And of course, its motion is governed by the gravitational potentials produced by the dark matters inside the galaxies. On the other hand, on the observational side, actually there are two different observations. One is a photometric one, which gives the information about some location of the member stars or something like that. And the other one is a spectroscopic data. And this gives us the information of the velocity of the member stars along the line of sight. And involving these two informations and comparing with the theoretical models, so we can estimate how the dark matter is distributed inside the dwarf spirals. And using these factors, the J factor can be evaluated. Or more precisely speaking, so the center mean value and its error are estimated as a posterior distribution function in the Bayesian analysis. So this is the point. And of course, this technique is frequently used. And already using these techniques, some people evaluate the J factor of dwarf spiral galaxies. But unfortunately, so it is also known that still some serious systematic errors are not correctly estimated so far. And actually, there are two important systematic errors not included at present analysis. So one is that the intrinsic error, which is coming from the completely spherical assumption of the galaxy. And the next one is something to do with the error from the subtraction of the foreground star, or background star, how to say, the foreground star, which is not belonging to the dwarf spirals, but located in the direction of the dwarf spirals. So how we can improve this one? And the first one is that we are thinking about non-sphericity of the dwarf spiral galaxies. And this is the actual data observing dwarf spirals at the telescopes. And the black dot is just a star observed at the direction of the dwarf of the galaxy. And the blue one is actually is a selected stars based on the very naive cut to choose the member stars. And the red points are also the selected stars, which is identified to be member stars using a very special statistical techniques, so-called EM method, like expectation maximal method. But the point is here is that this dwarf spirals doesn't look like completely spherical. But so far, all the J factor is estimated based on the completely spherical. So we wanted to improve this. And actually, so we have estimated the J factors of almost all dwarf spirals which are relevant to the indirect dark matter detections, assuming that profile of the dwarf spirals to be non-spherical, or to be more precise, the asymmetric, axisymmetric. And fortunately, our result is frequently referred at many talks and papers by not only theorists but also by experimentalists, including CTA people. And actually, this is the result of the J factor estimations at present. And this is just a case for Draco galaxy and Ursa Minor and Ursa Major 2 galaxies, and these two are called classical dwarf spheroidals, and the last one is called ultra-faint dwarf spheroidal. And the red one is our result, assuming the axisymmetric profile, while the purple one is the estimation of the J factor using the original method. And actually, for classical dwarf threads, there is no much difference, but of course, error is much larger than the previous case. So we have to include this kind of error correctly to put a limit on the WIMP property. And I have several comments on this result. One is that the asymmetric model always gives better fit than symmetric one, which is obtained by comparing the so-called Bayes factors between these two cases. And as I told you, so the central value of the J factor is not changed so much, but error is increased. And for the ultra-faint dwarf spheroidal case, the statistical error dominates. So it is very hard to say that what kind of merit we have, even if we take the axisymmetric model. But this is not the end of the story. So we have a more serious problems. So this is a so-called subtraction of the foreground stars, which is act as a background to estimate the J factor. And as I told you before, in many dwarf spheroidals, their J factors are estimated based on the blue ones, actually. And some very special dwarf spheroidals, some special techniques used, the red ones are used. And also, we have, propose a new way to correctly estimate the J factor. So I want to explain this one. And actually, the point is that we use the so-called simultaneous fittings of the member in the foreground stars in the analysis. And this method is the particle physicists are very familiar with this method, actually. So this is because we use this kind of method. First, so this is actually is a location of the dwarf spheroidals, but we also think about some region outside this one. And let's call that this red region is called the signal region, and this green one is called the control region. And actually, the background or foreground star contamination can be estimated by using the data in the control region. Or in other words, so the foreground contamination can be estimated from control region in the data-driven way. And this method is frequently used at LSE experiment, actually. And in this meaning, it's nothing new. But this is actually worked very well. And this is one of the results. So after taking this method, we get this kind of result. This is actually the distance from the center, and this is the velocity dispersions, and this is observed data in the simulation. And this is just a member star component, and this is a foreground star component. And the solid line is just our result, and the dotted one is just the input value. So from this one, we can understand that some input value can be well reproduced by using our method. And also, so this is a result of the J factors in the simulation. This is something. And this is a case for the classical dwarf spheroidals. And the blue one is our result. And the yellow one is J factors obtained using second method. And the green one is the J factors obtained by using this first method. And as we expected, if the J factor is estimated based on the naive cut, so always J factor is overestimated. On the other hand, in the second method, this method is frequently used in the astrophysical community. So it's not overestimated, but slightly different from the input value. And our method is well reproduced the input value. And also, this is a result for the ultra-faint dwarf spheroidals. Again, the J factors based on the first one, naive cut, overestimates the J factor. On the other hand, and actually this point is that if we have deeper observations, So we have this kind of result, and we have more deeper observation. We have the last one. So our method is, we can find from this figure that so our method is converging to the input values, and meaning that our method works in the statistically correct way. On the other hand, in the second method, actually this is not so bad, but how to say, is if we use deeper observations, then the results become a bit away from the input value. So there remains some systematic errors, I think. So actually, from the so-called LSC method works very well, even also for the estimation of the J factors. And actually, I want to develop this kind of method more, how to say, convenient way. Okay, let me summarize my talk. It's okay. First, the WIMP, which has a weak charge, attracts many attention now, especially after the Higgs discovery. And only indirect dark matter detections allow us to detect this type of WIMP in near future because of its heavy mass. And also, among the various indirect dark matter detections, the observations of gamma rays from dwarf spheroidal galaxies are the most robust way to detect the signal of, or at least to put a constraint on this type of the tape scale WIMP. And also, it is very important to predict the signal flux for this purpose, and it requires a very careful estimation of the J factors involving the treatment of the foreground, controlling the foreground star contamination, and also the dark matter and stellar non-sphericity. And the important comment is that in order to take this kind of our method, so we have to obtain the information of the spectroscopic information of the stars inside the red region, but also in the green regions. So meaning that we need the spectroscopic observations with a telescope having a large field of view. So in this purpose, actually, the so-called PFS project, PFS project in PFS in similar project at the Subaru telescope will play a very important role. But I don't want to explain this project very in details because the next speaker, Takada-san, will talk about the project itself. That's all. Thank you very much.